So hey guys, how are you? This is the video number 6 and we were continuing the group action. So in this video, we will try to understand the one more important theorem called the Cayley's theorem. So this is very nice theorem actually in the abstract algebra, and the statement is as follow, that it says that if G is a finite group and the cardinality of G is n, then G is embedded G is embedded in a Sn. This is the group Sn, the permutation group. This is nothing but the permutation group on n symbols. Okay, so it is saying that once we have any finite group of cardinality n, for that group G, actually that group will be embedded inside the group Sn. But what do we mean by the embedded here? It means that is there exists a 1-1 homomorphism, 1-1 homomorphism from our chosen G, from G to Sn. This we have to show. So before proving the Cayley's theorem, we have to understand a small observation here, and the observation is that we all know that we have a group action phi from G cross A to A. This is our group action, and and this acts on the element G comma A and sends to the again element of A, and corresponding to each element, corresponding to G in G, what we have a sigma G as we defined, sigma G a bijection on A. And how it is defined? It is defined as sigma G acts on some element of A and send this back to the element of A in this following fashion. So since we have the group action phi, then what we have its kernel. We have its kernel of phi. Also, since we have a homomorphism from G to SA in the way that G goes to sigma G as we defined earlier, then suppose that this homomorphism is psi, then what we have kernel of psi also. One can easily notice that they both are subgroup of G and they both are normal subgroup of G. Then what are the relation between them? And the relation is that they are actually equal. This is your homework. It is a very trivial exercise. Your homework is to show that kernel of the group action and the kernel of the corresponding group homomorphism from G to SA are actually same. They are the same kernels. Okay. They are the same in set also, in the set wise also. So using this result, we will try to prove this Cayley's theorem. So we have to show that there exists a 1-1 homomorphism from the group G to our permutation group Sn. It is a permutation group on n symbols. So let's see how we will prove this. So the proof. So the proof goes in the two way. So the first way, the first way is by the group action, and second way is also by the group action. But in both cases, the action will be different. First, observe that if I take the subgroup H, some subgroup H of G, and assume that G is finite, cardinality of G is less than infinity, and assume it is n. Okay. Now we can define a group action that G acts on the set of its cosets as we defined in the example number 2. Okay. And this map is suppose some phi, and phi takes the element of G and G by H and send it to the element of G by H again in the following way. This is the natural way we can define. This is just same as the example 2, and we have checked that the kernel of this group action is nothing but intersection of these type of sets. And we also proved that in the case that if H is normal, then it has to be H only. So now what can we deduce from here is that if I take H is the identity set, if this is just the identity set, then what will be the kernel? Then kernel of phi is also identity. Since kernel of phi is identity, then corresponding to this phi, as we defined, we have psi from G to SA. And what here is A is actually G by H. But since, okay, let me write it here. But since cardinality of H is identity, then what will be the cardinality of G by H? The cardinality of G by H is the same as cardinality of G, which is N. So the cardinality of A is also N. So I can replace this A by N. What is the use of A here? A just depicts the cardinality. So its cardinality is actually N, because A is here G by H, and cardinality of G by H is N, because I am assuming H to be identity set. So this implies that. And what was the kernel of the psi? And kernel of the phi was identity. So this implies kernel of psi is also identity. And since kernel is identity and psi is homomorphism, then this implies that psi is 1 1. Okay, so we got a homomorphism from G to Sn. Now, because I am replacing Sa by Sn, because they are equivalent, since the cardinality of A is N. And so we got a homomorphism psi from G to Sn. And this homomorphism is 1 1 also. So we can say that G is embedded inside Sn. So this is the first way proof. Let's see the another way. This is the second way. Second proof. For the second proof, what will we do? Assume, as we assumed earlier, that cardinality of G is N, which is finite, and define the group action phi from G cross G to G in the natural way, that phi of G1 comma G2 is equals to G1 G2, the product in the G as it is. Now if we see the kernel of this phi, the kernel of this phi is what? Those element in G such that which fix all element of G. But what is G dot G dash? It is nothing but just the product in the group. But if we look carefully at this, what does this mean? This means that G has to be the identity element E of G. Hmm? Why? Because this is just the definition of the identity element of the identity element of G by definition of identity element of G. Identity element of G. So this implies if G belongs to kernel of phi, then G has to be identity, and G has to be identity, and obviously identity belongs to the kernel of phi. So hence kernel of phi is just a trivial set, which is the identity set. So in this way, the kernel of phi is identity, and corresponding to kernel of phi, what we have? The kernel of psi is also identity. And what is here kernel of psi? Kernel of psi here is nothing but the kernel of this homomorphism G to Sg. But again, the cardinality of G is N, so I can replace Sg by Sn. We done it. So, but if you are unable to understand why this came out to be the identity only, this, then we can go by another way. How? we have to show that kernel of phi is equals to those element in G such that which fixes all element of G. But G dot G dash is defined as just the usual product in the group. Now suppose that G belongs to kernel of phi. Then what will this means? Then this implies G fixes G fixed all elements of G. In particular, in particular, G fixes G inverse. So this implies that G dot G inverse has to be G inverse. But this implies that G inverse is equals to G inverse. So again taking the inverse to the right hand side. So this implies G has to be identity. So this is also another way proof to show that kernel of phi is just the trivial set. So in this way we are able to show that kernel of phi is identity. We gave the two proofs. Okay. These are for the first proof is taking the H is equals to identity. Taking H is equals to identity in this group action. And the second proof is defining such group action. Defining this group action. And here the G is the same set A. Okay. So these are the two proofs to prove the Cayley's theorem through the group action. So thank you for watching.